Here is a small game with one rule. Write the number 1 as a sum of fractions, where every fraction is 1 over a whole number, and no two fractions are allowed to repeat. 1/2, 1/3, 1/7, that kind of thing. All different, all with a 1 on top. The question is not whether you can do it. You can, in many ways. The question is speed. With each fraction you add, you creep closer to 1 from below, and you never want to go over. So how fast can you close that last sliver of gap? What is the quickest possible way to add distinct fractions and land right on 1? It turns out there is a single best strategy, and it is the most obvious one you could think of, being greedy. At every step, grab the largest fraction you are still allowed to take. Follow that one instinct, and the denominators you are forced to use form a sequence that explodes in size almost beyond belief, while the gap to 1 collapses faster than anything else can manage. Let us actually play. We start at 0, and we want to reach 1, and the gap in front of us is the whole distance, 1. The greedy move is to take the biggest unit fraction that still fits under the gap without meeting it. The biggest unit fraction below 1 is 1/2, so take 1/2. Now we have used up half the distance, and the gap in front of us is 1/2. Repeat the exact same move. The biggest unit fraction below 1/2 is 1/3. Take 1/3. 1/2 plus 1/3 is 5/6, so now the gap is 1/6. Repeat again. The biggest unit fraction below 1/6 is 1/7. Add it, and the gap drops to 1/42. Notice the denominators we were handed, without ever choosing them on purpose. 2, then 3, then 7, then 43. We were only ever greedy, and yet a very particular list of numbers fell out. 2, 3, 7, 43. Keep going, and the next one is 1807. That list has a name and a rule of its own. It is called Sylvester's sequence, after the mathematician who studied it in 1880. And the rule connecting its terms is startlingly clean. Look at how each term relates to the ones before it. 2 times 3 is 6, and the next term, 7, is 6 plus 1. 2 times 3 times 7 is 42, and the next term, 43, is 42 plus 1. 2 times 3 times 7 times 43 is 1806, and the next term, 1807, is that plus 1. Every term is the product of all the earlier terms, plus 1. There is a second way to say the same rule that is even faster to compute. Take any term, square it, subtract the term itself, and add 1. Try it on 7. 7 squared is 49, minus 7 is 42, plus 1 is 43. The very next term. Both rules agree, always, and each one alone generates the whole sequence forever. Here is why greed produces exactly this rule, and it is worth seeing, because it explains everything that follows. Say you have already taken some fractions, and the gap in front of you is 1 over some whole number. After the first 3 moves, the gap was 1 over 42. The greedy move is to take the largest unit fraction strictly smaller than that gap. The largest unit fraction below 1 over 42 is 1 over 43. Because 43 is just 1 more than 42. So the new denominator is always the old gap's number, plus 1. And when you subtract that new fraction, the gap does something beautiful. 1 over 42 minus 1 over 43 is 1 over 42 times 43, which is 1 over 1806. The new gap's denominator is the old one multiplied by the term you just took. So the gaps are 1/2, 1/6, 1/42, 1 over 1806, and each denominator is the product of all the terms so far. Put the two halves together. The gap after any number of terms is 1 over the product of all those terms. And the next term is that same product, plus 1. That is the entire secret. The size of your gap and the size of your next denominator are the same number, off by 1. Now watch what that does to the gap, because this is the part that earns the word fastest. Each new term is essentially the product of everything before it, which means each new term is close to the square of the one before. 43 is close to 7 squared. 1807 is close to 43 squared. And since the gap is 1 over that growing product, the gap does not just shrink, it shrinks by squaring. 1/2, 1/6, 1/42, then 1 over 1,806, then 1 over 3,263,442. Think about it in terms of correct decimal places. After 4 terms, the sum is 1 point followed by a decimal that agrees with 1 to 3 places. After 5 terms, 6 places. After 6 terms, 13 places. The number of correct digits roughly doubles with every single fraction you add. No sequence of distinct unit fractions closes on 1 faster than this, because doubling your accuracy each step is as fast as this kind of sum can possibly go. It is one thing to say greedy is fast. It is another to say nothing beats it, and that stronger claim is actually true. Suppose at some step you got clever and refused the greedy fraction, taking a smaller one instead to save the big denominator for later. You would leave a larger gap right now, and here is the trap. The gap you leave becomes the whole budget for everything after it, and a bigger gap can never be closed faster than a smaller one. Falling behind once means falling behind forever. We can make this concrete. At the 4th step, greedy takes 1 over 43 and leaves a gap of 1 over 1,806. If instead you took the next fraction down, 1 over 44, your gap would be 1 over about 924, nearly twice as far from 1. And that penalty only compounds. This is a theorem proved by Curtis in 1922. Among all ways to write 1 as a sum of a fixed number of distinct unit fractions, the greedy choice, Sylvester's sequence, gets the closest to 1 from below. The price of this record-breaking speed is paid in the size of the denominators, and that price is enormous. The first 5 terms are gentle: 2, 3, 7, 43, 1,807. Then the 6th term is 3,263,443. The 7th term jumps to over 10.5 trillion. The 8th term has 27 digits. The one after that has 53 digits, then 105, then 209. Look at the digit counts alone. 1, 1, 1, 2, 4, 7, 14, 27, 53. Each one is close to double the one before. This is called doubly exponential growth, and it is far more violent than ordinary exponential growth. An ordinary exponential adds a fixed number of digits each step. This one doubles the number of digits each step. A few more terms, and you would be writing numbers longer than this entire video's script. A rule this clean rarely stays in one corner of mathematics, and Sylvester's sequence turns up in several. Start with a fact hiding in plain sight. Every term is the product of the earlier ones plus 1, so no term can share a factor with any earlier term. Any common factor would have to divide their difference, which is 1, and nothing divides 1 except 1. So the terms are pairwise coprime. That means each term drags in at least one brand new prime that never appeared before. Sylvester noticed this gives a clean proof that the primes never run out. One fresh prime guaranteed at every step. The sequence also answers a packing question, named after the mathematician Znam, about how few unit fractions you need and how close you can pack them under 1. And because the terms grow so predictably, their reciprocals appear in geometry, in the volumes and curvatures of certain higher dimensional shapes, where the same product plus 1 structure controls the arithmetic. The little greedy game turns out to touch number theory and geometry at once. So the fastest way to add distinct fractions to 1 is just to be greedy, and the sequence that falls out of that greed is Sylvester's. Every step you take, the biggest fraction you are allowed. The gap in front of you is always 1 over the product of everything so far, and that gap squares itself smaller at every move. The denominators pay for it by doubling their length each step, exploding into the trillions and far beyond, while the sum they build creeps to 1 with the number of correct digits doubling each time. And here is the honest ending. The sum never actually reaches 1 in any finite number of steps. There is always a gap, 1 over the product so far, however tiny. 1 is only the limit, the place all this speed is aimed at but never quite arrives. The fastest possible approach to 1 is an approach that never lands. That is the strange gift of being greedy. You get closer than any other method ever could, and you still never touch the number you were chasing.